as the atom. Studying the development of the atomic theory helps us to gain a better understanding of atoms and their structure and can help predict many of the properties of matter that we investigate. The modern atomic theory that we know today began to take shape in the early 1800s. In 1803, John Dalton proposed a model of the atom that was a solid sphere model. Dalton's atomic theory consists of 4 postulates or points. Number 1, all matter consists of tiny atoms that are indivisible. Number 2, atoms cannot be created or destroyed or divided into smaller particles. Number 3, all atoms of the same element are identical, and atoms of other elements are different. Atoms can be combined in definite proportions to form compounds is the 4th postulate and concludes Dalton's atomic theory. Now, this theory held true and realized that atoms of different particular elements differed from other elements. What it did not address is that atoms aren't divisible. They are composed of subatomic particles, which we will talk about shortly. In 1904, J.J. Thomson came up with the raisin bun model. Thomson revealed that there were electrons. He called these particles corpuscles. And these particles were present inside the atoms. He discovered this in 1897, and he won a Nobel Peace Prize for his discovery. He subsequently produced the raisin bun model of the atom. It shows the atom as composed of electrons scattered through a spherical cloud of positive charge. This model allowed us to recognize that electrons are components of the atoms. What it failed to do was identify something called a nucleus. And this model didn't explain later experimental observations. It's time to continue on discovering more about atoms. And we learn a lot more in 1911 with the discoveries of Ernest Rutherford. Ernest Rutherford's model contains a nucleus. He fired positively charged alpha particles towards a thin sheet of gold foil. Most of these particles passed through with very little deflection, but some deflected at large angles. This was only possible if the atom was mostly composed of empty space, with the positive charge comprised and concentrated in the center called the nucleus. This model was particularly favorable because it identified that positive charge was located in the nucleus of the atom. But still it wasn't perfect. It did not explain why electrons remain in orbits around the nucleus. Niels Bohr in 1913 came up with the planetary model. Niels Bohr modified Rutherford's model of the atom by stating that electrons moved around the nucleus in fixed sizes or orbits that had fixed sizes and energies. Electron energy in this model was quantized. Electrons could not occupy values of energy between the areas and must remain in the fixed energy levels. This model was favorable because it proposed electron orbits. However, this model broke down when we talked about heavier and heavier atoms. A complete model of the atom comes with the discoveries of Erwin Schrödinger in 1926. He came up with the quantum model. Schrödinger states that electrons do not move in set paths around the nucleus, but instead they move in waves. It is impossible to know the exact location of electrons. Instead, we have clouds of probability, called orbitals, in which they are more likely to find an electron. This model showed that electrons don't move around the nucleus in orbits, but rather in clouds. And it's still widely accepted as the most accurate model of the atom. Schrödinger wasn't quite the last word on the atom. In 1932, English physicist James Chadwick, a student of Ernest Rutherford, discovered the existence of the neutron, completing our picture of the subatomic particles that make up an atom. The story doesn't end there either. Physicists have since discovered that protons and neutrons that make up the nucleus are themselves divisible into particles called quarks. But that's beyond the scope of this post. At any rate, the atom gives us a great example of how scientific models can change over time and shows us how new evidence can lead to new models. Your responsibility for the history of the model of the atom is to identify each scientist and the name of their model and their main discovery. So, for example, J.J. Thomson came up with the raisin bun model, and he discovered the electrons. Ernest Rutherford, nuclear model, and he came up with the nucleus. Niels Bohr, planetary model, and he identified orbits. Let's look closely at Ernest Rutherford and his gold foil experiment. In 1911, a New Zealand-born scientist and a student of J.J. Thomson who studied at McGill University in Montreal, his name was Ernest Rutherford. Rutherford devised the gold foil experiment. His experiment involved aiming a beam of positively charged particles called alpha particles at a very thin sheet of gold foil. Now, this is what he expected. Based on Thomson's model of the atom, Rutherford expected that most of the positively charged alpha particles that were being shot through the gold foil would end up directly behind the gold foil at this location here. He created a screen that would glow brightly if the presence of these alpha particles was detected. And based on Thomson's model, if the electrons and positive charge were equally scattered through the atom, then this is what he would expect. All of these alpha particles to end up directly behind where they were shot through the gold foil. But that's not exactly what happened. Surprisingly, some of the particles were repelled backwards. Instead of passing straight through the foil, as if they were deflected by something large and positively charged. Some of these alpha particles bounced right back. And this was not expected because this gold foil is so thin. An analogy would be if you shot bullets through a sheet of tissue paper, you would expect all of the bullets to end up directly behind where you shot them through. So what was causing these bullets or these alpha particles to deflect in different locations? Based on this experiment, Rutherford inferred that a small region of extremely positive charge exists in the atoms of gold and repelled the charge of the alpha particles if they came close. Results: all positively charged particles in an atom form a small, dense center, and he named the center of the atom the nucleus. A nucleus is the positively charged center of an atom. So here's a model of an atom, and it still needs some work, because remember, after Bohr, there were still more discoveries that clarified this. But what we discovered in the gold foil experiment is that all of the positive charge exists in a tiny dense area called the nucleus. The nucleus is very small and contains most of the atom's mass. The negatively charged particles, the electrons, are surrounding the nucleus and occupy most of the atom's space. They're small and very light and contribute only a small fraction to the atom's total mass. So let's summarize the atom. After we discuss all of the history and the experiments, this is the most important part that you are responsible to know. All elements are composed of atoms, and an atom is the smallest unit of any element. These atoms are not indivisible anymore. They're composed of 3 subatomic particles. Sub meaning smaller than, and atomic meaning the atom. Subatomic particles are particles that are smaller than the atom. The nucleus, which contains the protons and neutrons, takes up most of the mass of the atom. So let's look at these 3 subatomic particles. Number 1, the electron, negatively charged and orbits around the nucleus of an atom in distinct energy levels. The second subatomic particle is the proton, a positively charged particle, and it's located inside the nucleus of an atom. Number 3, the neutron, an uncharged particle that is part of almost every atomic nucleus. So here's a model that explains everything we've learned thus far. We have 3 subatomic particles: protons, neutrons, and electrons. These electrons are found in orbitals or energy levels around the nucleus. Inside the nucleus, we see protons, the red particles, and neutrons, the yellow particles. The nucleus contains most of the mass. The rest, all of this area, is mostly empty space. And that's where the electrons reside, in these orbitals or energy levels. Here's a summary. Electrons are located in orbits around the nucleus, and they are negatively charged. Protons are located in the nucleus and are positively charged. The neutron is located in the nucleus and is neutral. It doesn't have a charge.